this is given as V over 8 pi cubed. Because we assume that the electrons are not interacting with each other, we can build up the n electron ground state by placing the electrons into the allowed 1 electron levels, that means the k points. Now, the 1 electron levels are specified by the wave vector k that we have here, and the projection of the electron spin about any arbitrary direction. So, we know that electrons are spin half particle, that means its projection are plus minus h cross over 2. This is the projection of the electron spin. What is the lowest energy, lowest possible energy for an electron? We have energy equals h cross squared k squared over 2m. So, if k goes to 0, then the energy would be 0. And we fill the lowest states with electrons first. So, the energy of the single electron level is directly proportional to k squared. When the number of electrons, that is capital N, in the system is very large, then it will the electrons occupying the lowest energy states first and then subsequently higher energy states, that kind of an arrangement will look like a sphere in the reciprocal space, in the k space. So, we will have a sphere with a certain radius. Let us call this radius in the k space as the Fermi wave vector kf. And kf is the radius of this sphere inside which all the k points, all the allowed k points are filled with electrons, outside which nothing is filled with electron, no allowed k point is filled with electron at absolute zero temperature. So, we have this volume omega for this sphere, which is nothing but 4 over 3 pi kf cubed, and this volume is filled. So, the number of allowed k values within the sphere that would be given as omega times v over 8 pi cubed, which is nothing but kf cubed over 6 pi squared times v, where v is the volume of the cube that we have considered as the size of the entire crystal. Now, since each allowed k value leads to 2 single electron levels, one for each spin, we have considered 2 spins here, then in order to accumulate n electrons, we will have n equals, so this is the number of total number of electrons in the system, it is twice kf cubed over 6 pi squared times v, which is kf cubed over 3 pi squared times v. So, if we have n number of electrons in a volume, then for volume V, the density of electrons would become n over capital V, capital N over capital V. Then the ground state of this n electron system, that would be formed by occupying all single particle states for the region k less than kf, and kf in this case, the Fermi wave vector, would be given as, so we can write n equals kf cubed over 3 pi square. This expression gives us the value of kf. The sphere of radius kf contains the occupied single electron levels, and this kind of a sphere is called the Fermi sphere. And surface of this sphere is called the Fermi surface. The momentum h cross times kf, this can also be called pf, which is the highest momentum, highest possible momentum at 0 temperature, is also called the Fermi momentum. And if we write Vf, the velocity of electrons on the Fermi surface, that is Pf over m, this velocity is called again the Fermi velocity. Finally, the energy of those electrons on the Fermi surface, that is the maximum energy, h cross squared kf squared over twice m, is called the Fermi energy at absolute 0 temperature. So, the total energy of the ground state system of capital N number of electrons can be obtained by summing over k less than kf and multiplying that with 2 h cross square over twice m k squared. So, if we sum a smooth function over all allowed values of k, we may proceed like the following. We have the volume of k space per allowed k value. So, the volume of k space per allowed k value, we are calling it delta k, that equals 8 pi cubed over v, as we have discussed earlier. Now, if we sum over k any function fk, smooth function, that would give us v over 8 pi cubed sum over k f k delta k. Now, if we have many number of electrons, a large volume of this cube, we will have delta k tending to 0, and that means the volume tends to infinity. then only we will achieve this situation delta K tends to 0. Then the sum, this sum here would approach an integral. So this sum can be written as integral d3k fk. So we can now rearrange and write limit volume tends to infinity 1 over the volume sum over k fk. This quantity equals integration over d3k over 8 pi cubed fk. So this is converting the summation to integration under certain condition that the volume tends to infinity. Then only this thing works. And this kind of formation is very useful in condensed matter physics. So remember this quite well. Now when applying this for finite but large system, we assume that our sum differs very little from the integration limit. We are considering from something finite, but we assume that our sum differs almost negligibly from this integral. And now using this to evaluate the energy, we find the energy density of the electron gas, that is E over V, energy per unit volume, equals 1 over 4 pi cubed integration over the limit k less than kf for absolute 0 d3k h cross squared k squared over twice m, which is 1 over pi squared h cross squared kf power 5 over 10m. So d3k, if we expand this in spherical coordinate system, we will get k squared dk kind of a term, and that will bring us k power 5, and provided this limit, we will have kf power 5, this kind of a term here. So to find the energy per electron instead of energy per unit volume, we can write energy over the number of electrons equals 3 over 10 times h cross squared kf squared over m equals 3 over 5 epsilon f, the Fermi energy. So by simplifying this in terms of the Fermi wave vector, we can write n over v as kf cubed over 3 pi squared. So this is the number density of electrons. The number density of electrons can be written in terms of the Fermi wave vector in this fashion. So we have discussed the electronic properties in the context of Sommerfeld model at the absolute 0 temperature. Now we will see what happens if we increase the temperature.